This is Project 23 of Hacking with Swift. We're back to SpriteKit again, and this time we'll make players pilot a spaceship safely through a field of space junk. For more information, see the website hackingwithswift.com, where you can buy this video and all videos in this series in fantastic high-resolution quality. You can also download this tutorial as an ebook, or indeed the whole series as an ebook, starting from just $3. Your support is so appreciated. It helps make more videos like this one. You can also find me on Twitter. I am at 2straws. If you have questions, problems, find a mistake in my code, get in touch. I'll do my best to help you. Let's get going. We've got lots to learn about. For example, advancing particle systems, linear and angular dampening, and even per pixel collision detection, which is a wonderful, fast technique to do really precise collision detection. Make sure you've already downloaded the code for this project. I've got it here for you already. You'll find helper.swift like usual, array+shuffling.swift, and also a content directory full of stuff. Make sure you have them all already. So let's go ahead and launch Xcode. You know, we're going to make this project, the entire thing, in less than 100 lines of code. Maybe just over 100 lines of code. Let's call it 100 lines of code. Super fast, efficient programming here. Choose iOS application game. And for the name, I will enter Project 23. Like that. Choose device, iPad, SpriteKit, Swift, next. Then create. Please copy in the files I gave you. So I'll choose all three of these things, drag them into my project. Make sure copy if needed is selected. Create groups and press finish. Deselect portrait and upside down, only landscape. And then in game scene.swift, zap the contents of did move to view and also touches began like that. You should also remove the spaceship picture from images exe assets like that. Okay, that's a clean project. Are you ready to go? Let's see what we can do in 100 lines of code and how fast we can make it happen. So start a timer. This is going to be awesome. Remember, make sure you choose iPad 2 for your simulated target, not iPad Air or Retina or resizable. iPad 2 is the best option, it's the fastest one. Okay, let's go. We're going to start off with the background. It's not going to be a picture this time, it's going to be a star field, stars whizzing by. So we can go to our game scene and create a property for it called var starfield is an SK emitter node. Like that, implicitly unwrapped. We'll also make a property to hold our player image. So var player is an SK sprite node, as well as a score label. Label is an SK label node, implicitly unwrapped, and also var score is an integer with a default value of 0 with a property observer like usual. Did set score label dot text equals score with some string interpolation. Score, boom. All old stuff. This is not new. That's not new. All old. But this time we're not going to use a background picture. So we'd normally say in did move to view, create the background picture and show it in there. We're not going to do it this time. Instead, we're going to give ourselves a background color of black. So we'll just say background color equals UI color.black color, and then create a star field in here. Now I've made one for you already, and it looks like this in content. You'll see starfield SKS. So things stream from the right to the left. And if you notice in the editor, there's a very, very wide position range of 768. So it will generate 384 down to 384 up around our center position. So you get this constant scrolling starfield, all different speeds, colors, and so forth. Get a nice dense looking starfield. So to make that work, we're going to say let starfield path equals ns bundle dot main bundle dot path for resource. Boom. It was called starfield of type SKS, and then force unwrap that. Then we'll say starfield, i.e. our property, starfield equals ns keyed unarchiver dot unarchive object with file, and use starfield path as SK emitter node. This is all old stuff. We'll position it like this, starfield.position equals CG point with a lowercase o, point, with X being the far right of the screen, so 1024, and Y being halfway up, so 384. And then, something new. we're going to call starfield dot advanced simulation time into 10 seconds. This means simulate 10 seconds worth of particles being created and destroyed and moved before doing anything else. I'll add that to our game, add child, starfield, and move it with its Z position to be -1. So it goes to the back of the screen. Let's run that back now, see how it looks. It should look pretty good to get us going. We'll go to landscape, all being well, because we want landscape. There we go. And there's a starfield, super fast. If we hadn't, by the way, had advanced simulation time, you see this beginning thing where the stars start all on the right and sort of stream in, which looks obviously wrong because this is not possible in space. Unless you're in a black hole, of course. So we want an advanced simulation time to sort of happening. So it'll basically generate 10 seconds of movement, more than enough to fill the full screen, more than enough. Like that. So that is our starfield up and running. Then we'll create our player. So after the starfield, we'll say player equals sk sprite node with image named, and it's called player. That. We'll position the player at a starting position of CG point with x 100, y 384. So halfway down the screen, a little bit in from the left. Then we'll give it a physics body. This is using the new pixel perfect collision detection, i.e. because the player is not square or round, you know, if something hits here in rectangular detection, that would count as a collision because the rectangle is all the way around. In a straight rectangle, it would look rubbish. With pixel perfect, it has to actually hit the exact pixels of the player picture rocket. It ignores transparent pixels, which is of course much more work. Has a lot of pixel detection, but this is important. SpriteKite is very good at it, so it makes it very fast. Now you're ready. This is complicated code. You've seen a rectangle and circle physics, which is quite easy. This is, as you'll see, much harder. Player.physicsBody equals sk physics body texture, like that, and then player.texture and size player.size, and that's it. Yeah, I lied. It's not hard at all. It's really easy. That is how you do pixel perfect collision detection inside SpriteKit. It is crazy easy. I love it. Let's now say player.physicsbody.contactTestBitMask equals 1. That means tell us when we collide with things that have the category of 1. Bitmasks we do much more in detail in, say, we've done actually already in one of the previous projects, but we'd go into, I think, full detail in 29. But realistically, this is a very simple game. The player can only collide with the other things in the game, i.e. the space debris they'll find as they fly around. So 1 is fine. Add child player. And then finally we'll create a score label, which is just old code. Score label equals sk label node, font named. This time I'm not going to use Chalk Duster. I'm sick of Chalk Duster. Just kidding. Chalk Duster. And then I'll set a position to be position equals CG point x16, y16. So the bottom left corner of the screen. Remember, SpriteKit counts from the bottom up. Then we'll align to the left. Score label dot horizontal alignment mode equals dot left. And add that to our scene too. Score label. Now this time I'm just going to say score equals 0. That will actually trigger the property observer. It's a much easier way of doing the default score label. Finally, I'm going to turn off the gravity in the game. I don't want gravity. So I'll say physicsworld.gravity equals CG vector make. Oh, sorry, vector dx 0 dy 0. No gravity, because there is no gravity in space. Now, of course, there are some astrophysicists out there, or people who stayed awake during their school, who know that, of course, there is gravity in space, otherwise everything would go very wrong. But it's very complicated gravity, pulling in many directions simultaneously, so for all intents and purposes, we just nil the gravity. And finally, we make ourselves the contact delegate for the physics world, which, of course, it'll cause complaints straight away, because you have to implement the protocol, or conform to it, sorry, sk physics contact delegate up there. And that is our basic scene. I'll press play so you can see how it looks. You should see a player, there we go, and a score, and our stars. That was very easy. Next up, let's look at the enemies, because the enemies are also quite straightforward. I've given you 3 pictures to work with, all different shapes. We've got a big basketball, which is nice and round. We've got a hammer, which is completely uneven, and a TV, which is square. Now you could very easily say, give this one rectangle physics, give this one ball physics, and give the hammer, pixel perfect physics. And that is, of course, faster, more efficient to do exact different types of physics per element. I'm not going to bother with that here because that's a bit more work than I want to do because I'm quite lazy. This is, of course, hacking with Swift, not very careful coding with Swift. So we're going to go back to our scene here and create a little property to handle all the possible enemies. So we'll say var possible enemies equals its array of ball, then hammer, then TV. So one of those 3 things can be enemies. We're also going to use another timer. So I'll do game timer is an NS timer. We used this before to create fireworks at regular intervals. This will create enemies at regular intervals. And then I'll create a new boolean called game over. Is the game over? Because the way the game's going to work is, as long as the player is alive and has not hit any sort of space debris, game over is false. And we increment the score all the time. So the scoring points, until finally they hit something, at which point they die and the game stops. Game over becomes true. Okay, so we need to create enemies from this list of possible enemies every so often. And I'm going to use about 1/3 of a second. This is from, again, careful playtesting, i.e. just playing the game lots. So I'll say, game timer equals ns timer dot scheduled timer with interval. Choose the target selector version, not invocation. And then for the interval, 0.35, so about 1/3 of a second. And then target is self, selector is create enemy, user info is nil, and repeats is true. Keep on creating enemies till I tell you to stop. So this is straightforward. You've done most of this already. There's only a couple of new things here. Firstly, shuffle the possible enemies array, because we want to just create the first thing we see, but make it different every time. Then position it off the right edge of the screen so it sort of flies in from the right. Give it a random vertical position, then add it to the scene. That part is old. The new part is this. We have to create pixel perfect physics again, then tell it to climb the player, then make it move left at a decent fast speed, and then give it some angular velocity. But most importantly, we have to modify its linear damping and its angular damping. These are new things. I haven't used these before. So when something exists in the physical world, even without gravity or anything else like that, even though we know it's space, SpriteKit does not know it's space. And what happens is if you give something a spin, which is a good thing. We had it in our Fruit Ninja game, if you remember. It's a good thing to have spin. You want the hammer to spin round, so it's nice and hard to know where to move to. But SpriteKit will slow it down over time. It'll say, well, listen, you're obviously in air because this is a physics world. I should slow you down over time, make your spin slow down. So over time, it has a nice big spin to begin with, but over time it slows down. So the game looks strange because, of course, there isn't a whole lot of friction in space because it's space. So we're going to have this modified by using linear damping, don't slow down over time in its velocity, and angular damping, don't slow down its rotation over time, because we're in a frictionless space environment. So let's make the create enemies method. Create enemy. So first up, shuffle the list of enemies. That's easy to do. You have this from the array plus shuffling Swift file we imported at the start of the project. Then we'll pick the first one. So we'll say let sprite equals SK_sprite node, image named, the first thing of our array. So we'll say possible enemies 0. So we've shuffled it, so it'll be a random thing at the beginning. Then move it off screen, and I'll do position CG point is X 1200, and then Y is down to you, but I'm going to use a random number. So let's put it well off screen, because of course some of them are quite big. I'll use a random number between random int. I'll use min 50 and Y 736. That just spaces them out nicely on the thing. In fact, that's a bit of a strange number. It should be 738, shouldn't it? Yeah, 738. There we go. Even that isn't right. I can't do basic maths. Oh, sorry. I think you can have it this way. I've got it at min 50 here because of the score label at the bottom. This keeps it spaced from the top a little bit. That keeps it slightly more spaced from the bottom, but it's really down to you. Anyway, now let's look at the next bit, the important bit, the new stuff, which is the per pixel collision detection. So I'm going to add that thing to our scene. Add child sprite, like that. And then say sprite.physicsBody equals sk physicsBody, sk physics body, with a texture being sprite.texture and a size being sprite.size. That's easy enough. I'll give this the same bit mask I used for the contact up here, which was here. Contact test bitmap. This means collide with things that have category 1. So I must say down here, sprite.physicsBody.category bitmask equals 1. I am a type 1 object for collision purposes. Then give it a nice velocity. So I'll say sprite.physicsBody.velocity, give it a good nudge, equals CG vector x minus 500, y 0. So it moves straight to the left at a speed of minus 500 units. Then I'm going to modify its spin. So they all spin slightly. Sprite.physicsBody.angular velocity equals 5. And finally, the two new things, linear damping and angular damping. So sprite.physicsBody.linear damping equals 0. Don't slow down your velocity over time. And sprite.physicsBody.angular damping equals 0. Don't slow down your rotation over time. That's it. So you can go ahead, you can run that now and press play. You should start seeing lots of bad guys appear on the screen. There we go, a hammer, bonk. Lots of space debris flying around, hopefully none below score, so the score is always visible. Yeah, look at that, that's just perfect, beautiful. So that's our basic space debris working. There's a slight hiccup here, which is that we aren't removing them from the game once they go off the screen. So that's easy enough to do. In the update method here, we can just whiz through and remove it from the parent as needed. So we'll say in update for node in children as skNode, like that. If the node position dot x is less than minus 300, i.e. if it's 300 points off the screen fully, just to make sure some of these things are quite big. Oh, that's minus 300 even. Then node.remove from parent. Get off the screen entirely. So that just cleans up the thing as the game happens. And then also every update, every tick of the game before we draw anything, if game over is not true, so if it's false, then score plus equals 1. So add 1 to the score, which updates the score label. Press play, and the game starts to come together. Score's taken up nicely, flying along. Bonk hits the player. Obviously a bad thing, we've lost the game, but it carries on. Okay, so that's our basic stuff. Let's look at how we do actual collision detection. This is very straightforward. You've done most of this already. And to begin with, we want to give the player a chance to survive. We want to make them able to avoid dying, because that's obviously the fun of the game. So what we'll do is we'll use touch as began. As they move around on the screen, we will move their player. Actually, we won't use touch as began. We use touch as moved. Touch as began is when you touch the screen. We'll use touch as moved. Much better. So when they move their finger on the screen, update where they are. So first up, we do the usual grab a touch. We say let touch equals touches dot any object as UI touch. That's old. Then where's it been touched? So var location equals touch dot location in node self. That's also old. Now, what we're going to do is we're going to clamp the user's movement so it can't move beyond a certain point of the screen. So we're going to say if location.y is less than 100. So if they're trying to go right to the very bottom of the screen, i.e. to dodge our debris, don't let them do that, because obviously that makes the game rather easy. You can just hide off the screen next to the score label and they'll live forever, which is bad. So we've got extra parenthesis there. If it's less than 100, we'll say location.y must be 100. Else if location.y is greater than 668, sorry. So that's 768, the height of the screen, minus 100. Then location.y equals 668. So make it so they can't get below 100 on either side of the screen. And finally, we'll just say player.position equals location. So now they've got a chance at playing. That was quite straightforward. Press play again. I can tap and drag around, and I am moving around trying to avoid the hammers. I'm dead. Yeah, I'm dead now. Fine. Okay, so but you get the idea. That's the point of the game here. So easy enough. We're now going to look at what happens when the collision happens. So we've got this contact test bitmaps set up already, which means it will tell us when a collision happens between the player and one of the bad guys, a TV, a hammer, or a basketball. Obviously, the things you find in space. Zap this empty touch as we can method because it's pointless. And then we'll add in the extra method. So down here somewhere, beneath update, we'll have did begin contact. So a collision's happened. We've told it there's only one thing that can collide, the player, and one thing that can collide with, the bad guys. So we're going to have to zap the player when this happens. So we'll say let explosion path equals nsBundle.mainBundle.path for resource. Really, this should be just so much easier, but it isn't. Explosion of type SKS, force unwrap. Let explosion equals ns-keyed unarchiver.unarchive object with file, and it's called explosion path as sk emitter node. Explosion dot position equals player dot position. So wherever the player was when they got hit, and add that to our scene. Explosion that. Finally, player dot remove from parent. Of course, the game is now over, so we should say game over equals true. That's it. Believe it or not, that is it. Now I said 100 lines of code, but I've got some comments at the top here. Look, if I delete those, they don't count as code, surely. Oh, look at that, 98 lines of code. I just squeak under my limit, and that finishes the game. Believe it or not, that finishes the game. If I run it back now, I've actually got a real working SpriteKit game under 100 lines of code. Here are some hammers, and I move around, dodge that TV, and come under here. Can't go too low because it doesn't let me, it clips my movement. And go up above that, and down, I'm doomed. Bang, I lose. 607. Not bad for a second go. And that's the game. Boom. That was so straightforward. And yet you learned about pixel perfect collision detection and angular damping and advancing particle simulation. That is how amazing SpriteKit is. That's the game over. For more information, see the website hackingwithswift.com, where you can buy this video in high resolution and admire beautiful high resolution basketballs and hammers and such. Or as a downloadable ebook, which contains more information to help you work your way through in a more leisurely way. It's all about speed and minimum lines of code. They cost just something like $3 a pop. Your support is so appreciated. Thank you so much. So please do buy one of those. You can also find me on Twitter. I am at 2straws. If you have problems, questions, or better graphics for my games, please do send them over. Follow me there. Get in touch. I'd love to hear from you.